So our next talk will be really under the hood, because that's about the Python client. I've heard about that client we used to have before the May, but the version has many, I would not say issues, but the wish list of people who used that was really long. And so here is the updated Python client, and Ivan, as one of the main developers of that client, will tell us more how can it be useful for you if you need Python client. So Ivan, please, I'll leave you on the stage.
Okay, hi everyone. Today I'm going to tell you about the brand new Python client for Apache Ignite. Previous release 0.3.4 was released almost 2.5 years, and there were a lot of bugs and feature requests, and I'm trying to explain something under the hood of each of these new features and demonstrate you some benchmarks, figures, and show you code examples. Okay, about me, my name is Daschinsky Ivan. I'm an Apache Ignite committer and Apache Ignite Python thin client maintainer. Here you can see my email, GitHub profile, and Telegram. Okay, what's new? First of all, we have a lot of performance improvements, really a lot, and in some scenarios, and these scenarios are not synthetic, it's common scenarios, performance improves about few orders of magnitude. It's and I will show you figures and benchmarks to prove my statement. Okay, the next one, support of partition awareness. Partition awareness, in few words, is simply redirecting Ignite request, thin client request, to cluster server node. Cluster server nodes distribute data across cluster, and some of the nodes contains so-called primary copy of this data, and so if we redirect this request to this affinity node, we can eliminate extra network hop. So theoretically, it can improve your performance, and I show you that it's really true. The next one, we have support of asyncio. So our thin client is also asyncio client. We support both synchronous and asynchronous versions of the client. And we have also implemented support to cluster API, activation and deactivation. This is very important, especially for persistent clusters. So let's start with a simple synchronous Ignite examples. Okay, here you can see the definition of the data. This is schema data. We define schema of student and type name. And you can see how to use synchronous version of client. You connect to the cluster using a special context manager, connection context manager. So you shouldn't call close explicitly. You create cache, you put data to the cache, and query Ignite using SQL and scan query. Okay, it's time for examples and for live code. This is Jupyter Notebook. I've launched Ignite locally using Docker Compose. So let's query. Okay, we import some necessary stuff. This is cache config. We create cache that contains concatenate our data, and we also create indexing on it. So we can query using SQL this cache. Okay, define student, define data, create client. Okay, let's put some data. I use pandas in order to pretty print data frame. Okay, we've put our data and retrieves it using getAll. Everything works. This is scan query. Notice that previous version contains no cursors that will simply generate, but nowadays cursors can be closed and contains context manager. So if something bad happens, cursor will be closed on the server side. Okay, everything works. And this is SQL. Select star from student. And it also works. Okay, let's play with cluster API. Here we set state to cluster active. For in memory, it's active by default. And we modify our data. Everything works. So let's try to change our cluster state to active read-only. And we got an exception. Yes, because cluster is in read-only mode, but we're trying to modify data. Okay, let's activate cluster and modify data, and voila, everything works. Let's return to our slides. Okay, before showing your benchmark data, let's take a few seconds to explain on which environment these benchmarks were run. So basically, it was 4 nodes, caches without backups, 8 gigabytes of heap, and 18 gigabytes of in-memory data region. Apache Ignite 2.10 and Python 3.8. Okay, let's talk about optimizations. This benchmark will measure putting byte arrays from 1 kilobyte up to 10 megabytes to Ignite. Ignite isn't very good when you're trying to put something big. Namely, Apache Ignite data page is in Apache Ignite page memory. It's about 4 kilobytes usually. But we will see that performance is reasonably good. Blue column is for old version, orange columns is for new version, and y-axis is in logarithmic scale in milliseconds. So you can see putting 4 kilobytes in old version takes 4 milliseconds, but new version only 320 microseconds. Huge difference, isn't it? And what about bigger data for the old client? Unfortunately, I was unable to proceed this test because main Python process hangs indefinitely. But as you can see, even putting a large amount of data, for example, 10 megabytes, it's not very good for Ignite, took only 57 milliseconds. I think it's quite good result. And what about retrieving data? Maybe things get wrong? No. We can see quite reasonable performance, and you cannot see data for old version the same reason, because of the same reason. And what about so-called binary objects? Let's put this data. Data contains indexed field ID and some byte array, something you can serialize, for example, using anything, message pack or CBOR or protobuf, whatever you want. And let's measure this performance data size from 1 kilobytes up to 1 megabyte. And you can see that performance of old client is pathetic. I have not any other words to describe this. 63 milliseconds to put 10 kilobytes, but new version less than half of milliseconds, 472 microseconds, and also reasonably good performance for even large object, binary object. And what about retrieving data from cache? Okay, performance from of the old client is slightly better, but also pathetic. And how have we achieved this? First of all, we have optimized memory consumption. We use bytes IO widely, we use memory view, we use byte array. The old version uses simply byte string, and during serialization just concatenates them. And you see the results of it. But how can we explain better results for binary object, worse than byte array for a low client? Okay, binary object has some format, and you must calculate hash code of bytes that you received after full serialization. And in the old client, hash code was implemented in pure Python, and this is not a good idea. This task should be implemented in C, and in the new version, I have implemented Python extension in C. Okay, I can demonstrate this. Here we have fallback in the pure Python. If you cannot compile C utils when you're developing Ignite or something like this, because of we shipped our Ignite with already precompiled binary for Windows and Linux. And if you will install Ignite using pip, everything will work out the box. So this is simple algorithm from the Java. In the Java, this is the way how hash code of string or byte array is calculated. So let's create some data 1 megabyte, and let's time calculation 1 second. This is optimized version. This is fallback version. And as you can see, 1 megabyte calculation. 1 second. Oh, okay. 1 megabyte in the C, calculate hash code of 1 megabyte calculated in about 1 milliseconds. But in the Python, it calculated 687 milliseconds. An order of magnitude. What about string? This is not a very big string, but in C it took only 200 nanoseconds, and in Python it took about 47 microseconds. Okay, let's continue with our slide. Let's talk about partition awareness. As I mentioned before, this is simply redirect to the affinity node of a cache request, and in this diagram, sequential diagram, you can see this process in details. When client firstly connect to the cluster, or if it's determined that his partition mapping is outdated. Partition mapping is map of the partition. Partition is a collection of key value, and every partition maps to the specific node, primary copy. And if you have backups, if you configure cache with backups, backup copy maps to another node. So
I'm so sorry, but the sound went wrong again. Can you please check it?
Your sound is very bad. Maybe you have a problem with connection. I've checked my connection and everything works exceptionally fine, and I have no problem with internet. Maybe someone can print. Okay, so client create first request to random node and get a response with the latest version of topology. Then, if client determines that its topology, this partition mapping is outdated, it requests from random node the new mapping, then determine the affinity node using this simple calculation. Just calculate hash code of the key, then map partition to the key, then map find from the mapping the affinity node, then redirect cache request to the affinity node. Let's see the figures from benchmark. So you can enable partition aware using this parameter of the client constructor. And of course, you must connect to the multiple nodes, and your connection parameters should contain the list of the nodes of the cluster. This is logarithmic scale, and the left, the blue bar is simple without partition awareness, and orange bar is with partition awareness. And for example, for excuse me, something interrupt me. Excuse me, I have some problem. Excuse me, something interrupts me from another backstage. Excuse me. Okay, let's see the figures for about for example 200 kilobytes. We see without partition awareness, it's about 2 times faster versus with partition awareness, and especially this is true for the large amount. 10 megabytes, 63 milliseconds versus 38. We just eliminate network hop, so we see the result. The same picture is for put byte arrays. And for binary object, you can see the same picture. So you should consider using this partition aware, this feature, and in some circumstances it can get even better results. And next is asyncio. Okay, if you don't know, there are some problem with concurrency in Python. First of all, Python use GIL, not only CPython, but also PyPy and many others. As far as I know, only Jython doesn't use GIL because it's based on JVM. What is GIL? It's when your thread is executing Python bytecode, and interacting with Python interpreter, Python data structures, it must acquire GIL. GIL is simply binary semaphore. When your thread goes to I/O, it releases GIL, but when your thread is going to process some data receiving from the socket, it must acquire GIL. So we write code to process the data, so GIL is obviously a bottleneck. And because of GIL, usefulness of multithreading, I think, is questionable. There are a few cases where multithreading can help, but in most cases, there's no benefit to write multithreading client to Ignite, for example. And is there a solution if you want to perform concurrent requests or process concurrent client request? Yes, of course, there is a solution. The event loop. Event loop is a single thread, but it uses not blocking I/O, for example, YPL for Linux. And Python introduces concepts of coroutines, and if you don't write a callbacks, you write a simply serial code, but using some construction, async, await. But of course, this user space scheduling and this extra syntactic sugar is not cost-free. But if you run I/O-bound tasks, many tasks in coroutines concurrently, you really can improve performance. I will show you figures. Okay, this is a simple example of async I/O client. As you can see, this code is serial and almost the same as the synchronous version. But as you can see, there are some constructs: async, await, async for, async with. Yes, we implemented async context managers, async cursors, and you can use all these pretty nice constructions. So let's see an example. This is Jupyter Notebook. Almost the same code, except that we import asyncio. Define student, defined data, and create asyncio client. Just add IO before client. And let's put some data and schedule our coroutine and get a result from it. As you can see, everything works okay. Let's play with scan query. As you can see, there are some peculiarities with asyncio, but nevertheless, code is the same as the synchronous client version. Here we are. There is data, and let's query SQL. Okay, everything worked fine. Let's continue to our slide. Okay, a few words before benchmarks. I use UV loop in benchmarks. This is a drop-in replacement of default event loop that's shipped with standard Python CPython implementation. This is Cython bindings to libuv. libuv is a core of Node.js and probably the fastest event loop implementation in the C, but only for Linux and the macOS, as far as I know. And you possibly have already used it if you're working with asyncio and writing asynchronous web services. So I think it's better to test against it because it's more realistic. So benchmarks almost the same, except that we added budget requests using construction asyncio gather, put budget. This is simply concurrent. We simultaneously create batch of the tasks and run it concurrently. And let's see, what does it mean if we are talking about performance. Okay, this is results. Scale is not logarithmic, it's linear, and this is microseconds. Okay, blue and orange bars far left is the synchronous client. Green and red is asynchronous client with and without partition aware. Violet and brown, 5 coroutines in batch. Magenta and gray, 10 coroutines in batch. And olive and blue, 20 coroutines in batch. Let's explain this data. As you can see, batched version performs always better than not batched for asyncio. But if you use partition aware, you use simultaneously many connections to Ignite, not only one, as in simple version. So you can create concurrently and use concurrently many sockets. And as you can see, there are quite good performance boost. For example, if you use 20 coroutine batch for partition aware, it performs 60 microseconds faster than if you use synchronous partition aware version. I'm talking about 1 kilobytes data. So you can analyze this. I will provide a link to these benchmarks, and you can see that partition aware is the must for asyncio. What about get byte arrays of large chunks? Okay, we see that for 10 megabytes partition aware, synchronous version performs really slower than asyncio partition aware with 20 coroutines in the batch. About 10 milliseconds you can save. The same figures for put byte arrays. And what about binary objects? As you can see, almost the same. So, conclusions. Partition aware must be enabled with asyncio because it's not only eliminates extra network hop, but it have some hidden features, connection pool effect. So please use this feature if you use asyncio version for our Python client. Okay, let's talk about our future plans. Expiry policy, TTL. This feature is already implemented and is already merged to master. And I think this is the most basic feature of every cache. And it's not good that this feature wasn't implemented earlier, but okay, we will release new version in a few months, I think in the summer. So, but nowadays you can use master version. It's stable enough. Then I'm planning to implement transactions and connection pools. Because I suppose that if we connect to each node using a few connections, and we use not 4 but 20 connections for different Ignite nodes, we can improve even better our asyncio performance. And I suppose that we should also implement some hacks in our deserialization and write some more C code. But I think it quite for plans, not for the next release. So this is the links. GitHub, Mir, read the docs, links to the benchmark, links to this talk, and you can always install PyIgnite using pip install PyIgnite equals 0.4.0 and try it right now. Thanks a lot. That's all.
Thank you, Ivan. And if you try the Python client, don't forget to give some feedback. I think that to user list, email to user list will be okay. Right?
Yes, and if you want, you can create issues in GitHub. I also read these issues, and you can contact me personally using Telegram or writing email.
Yes, I think that on the dev list or on the presentation, you can find the email. And Ivan is at the moment like a maintainer of that feature. Have you ever explored the machine learning related topic in relations to a Python client? I wonder what APIs our Python client should support to make it easy using Ignite with the ecosystem of a third-party Python frameworks, which are mainly for machine learning and data science.
Okay, but fortunately, I'm not a very good expert on Ignite machine learning. And for example, you can put to the caches serialized pandas data frames or something like this, and run some machine learning jobs using existing ML capabilities of Apache Ignite. But our thin client protocol, I'm limited with it, so I cannot do something that exceeds capabilities of this binary protocol. And our thin client binary protocol is about cache API, SQL, scan queries, and so on. So it depends. Please, if you create issues and create feature requests using Jira, and maybe I can implement something. But nowadays, this is not the main goal of our Python thin client. It's this client is for web applications, mostly for web applications.
But that's a very good idea for your first contribution to Apache Ignite. So maybe. If someone is interested, I think that's a good point to start.